Right, hi. Well, welcome to the Functional Safety Workshop. I'd like to introduce Edith Holland to you. It says here that after graduation, Edith joined Jaguar Cars and worked on projects related to functional safety in several departments across powertrain, chassis and electrical engineering. She's currently lead engineer for functional safety within the Jaguar Land Rover electrical, electronic and software engineering department. So, yeah, that is. Over to you.
I'm a lead functional safety engineer at Jaguar Land Rover, where I work in the electrical, electronic and software engineering department, as has already been said. And I currently work on the advanced driver assist projects, advising the functional safety activities and also setting functional safety processes for these projects. In my presentation today, I'm going to first start off with a bit of an overview on functional safety in general and also ISO 26262, the functional safety standard in the automotive industry, and introduce you to some of the concepts in it before going into the main part of the presentation, which is going to cover functional safety activities across the development life cycle from design to verification. This is ISO 26262, the functional safety standard for the automotive industry. It was published in November 2011. It was written by a consortium of international experts from the automotive industry. It's the industry-specific standard for the automotive industry, derived from the more generic standard IEC 61508. The second edition of it is already currently underway and should be published in 2018. It's got 10 parts addressing all aspects of the V-life cycle for automotive, electrical and electronic systems, and I'll talk a bit more in the next slide. What I did want to highlight as well here, actually, it's not a legislated standard, so it's not something that we need to show or prove to a regulator somewhere. It's considered to be best practice, and in case there was ever any litigation, it would be seen as state of the art. So that's really the motivation behind it. These are the 10 parts. I think we saw them already earlier in a presentation briefly by Jean-Marc with the V life cycle. 10 parts originally. There have actually been some additional parts currently published as PAS. They will be incorporated into the second edition. Expanding the scope downwards towards semiconductors and also overall towards including motorcycles and trucks and buses, whereby the first edition was just aimed at cars. The 10 parts cover the vocabulary, so general part, management of functional safety. I think you can just about read that in the color. Product development, the main part, the sort of meat of it, concept phase, product development at the system level, hardware level and software level, get a part each, and also covering production and operations or in service. Parts 8, 9, 10 include supporting processes and some more information on safety-orientated analysis. Right, so how does ISO 26262 tell you to do functional safety? It all is based around an item, which is quite an interesting concept, because an item is defined in the vocabulary section as a system, with a system assumed to include usually at least a sensor, a controller and an actuator, but it also allows a system to be an array of systems, so it could actually be placed at quite a few different levels. The vehicle could be a system, but it is actually very difficult to use the standard at that level. Once you've got your item designed, you analyze it, you do a hazard analysis and hazard classification. And for this, it contains a risk classification scheme using ASILs. ASIL stands for Automotive Safety Integrity Levels. They go from A to D, with D being the highest and A being the lowest. There's also a classification QM. QM stands for Quality Management, and that means that the item is actually not safety related, and normal quality management processes are sufficient for the development. Once the ASIL is established, this determines an approach to reducing risk, and that's similar to IEC 61508. There is the aspect of deriving and implementing safety requirements that define how the system should define safely, requirements what fault detections is required, and then secondly, processes and process rigors that you need to meet when you implement these requirements you've derived in aspect 1. The higher the ASIL, the more rigorous the process is the concept here. What ISO 26262 does acknowledge, what I haven't said yet, is as the OEM, we, Jaguar Land Rover, don't really go into any detailed design, any hardware, software design. You'll realize my presentation is at a much higher levels than some of the other presentations we've heard today so far. I mainly work sort of in the area of part 3 concept design. But ISO 26262 has got this, the automotive supply chain in mind, and has split the development up. So the different parts can be used by the different organizations involved. So we've got the OEM, in my case, Jaguar Land Rover, working concept design, possibly system design as well. It does depend on the type of system. But definitely hardware design and verification, software design and verification is always done by the supplier. It could actually be a tiered supply chain as well. So we could have a tier 1 supplier and a tier 2 supplier sharing responsibility here. The relevant verification activities that relate to design are obviously also done at this supplier level for the lower level activities. The safety case and the functional safety aspect is owned by us, so we have to gain all the evidence and convince ourselves that everything has been done appropriately and correctly. Just see. This next slide is just trying to illustrate this workflow a little bit more. So ISO 26262 assumes a generic system to look something like this. So I've got a sensor element, a controller element, and an actuator element, each consisting of some hardware element and software elements. So as Jaguar Land Rover, we analyze the system, come up with all the hazards, and we'll set safety goals. So for us, the safety goal is always at the vehicle level. It's the vehicle level behavior we want to achieve to convince ourselves the system is safe. The safety goal gets refined into functional safety requirements. So we're now defining behavior that needs to be achieved by these elements. So it could be assigned to all 3 elements. It could also just be assigned to 1 or 2 of them. Functional safety requirements as indicated by the yellow box. They're still sort of describing logical level behavior to achieve safety. The technical safety requirements are then a little bit more detailed and describe more sort of a design solution. And these are then allocated to either hardware or software as appropriate, shown in those pink boxes. What I'm next going to go into, so when you're down at the software and hardware development, you've got a part each, part 5 for hardware, part 6 for software, that shows very specifically the requirements for design and verification. Part 6 I'm going to cover first, so software development. It's got its own reference phase model for software development and covers the whole software development process. It's got guidance for selection of appropriate development methods and tools, some guidance on architecture design, unit design, and the relevant verification and testing for unit and integration with requirements on test methods or test coverage, for example. All these requirements are dependent on the ASIL of the requirement that's implemented in software, and as mentioned earlier, the higher the ASIL, the more stringent the methods are. They're still defined sort of not in absolute detail, but there is an indication in the standard that semi-formal or formal methods might be sort of more appropriate the higher the ASIL is, but it doesn't tell you exactly what it is that needs to be done. Hardware development next. Similar to software, part 5, the hardware development part covers the whole hardware design process, from architectural design and detailed hardware design. What we do have to be careful as an automotive company, we're still very much coming from a mechanical background, so we're here talking about electrical hardware. We have to often clarify it's electronic hardware components, not the metal bits of the car. Part 5 has got guidance for derivation of functional hardware safety requirements. For example, from the system level, we might cascade fault-tolerant time intervals to the hardware, and these must be met when designing hardware components. And these next 2 bullet points address hardware failure rates. So we're now sort of talking about the random hardware failure rates that were mentioned in some of the earlier presentations as well. Unlike IEC 61508 and some other standards, for example, in avionics, there isn't an overall target failure rate in the ISO standard, but there are some targets where, for example, the first one, evaluation of effectiveness of hardware architecture to cope with random hardware failures, we do have to show some numbers effectively. So diagnostic coverage is calculated for single point failures, residual single point failures, and latent faults. And also probabilistic metric for random hardware failure, PMHF, that evaluates the residual risk of safety goal violations. Although there's actually 2 methods for that, or you can evaluate it by looking at each case. It's a cut set analysis, and failure rate classes like FMEA are assigned and have to meet certain targets. So to summarize, really, for us, it's we consider it mainly supplier responsibility to meet these requirements of ISO 26262, the process compliance, where the development process needs to be compliant with the ASIL, and that is applicable for system, software and hardware design. And then, of course, the hardware failure rates, we don't tend to get involved at that level of design. We don't tend to get the information even, or see the information that would enable us to look into this detail and determine failure rates and failure modes, and failure rates. So this is also a supplier responsibility to determine the single point, dual point, and latent failures, failure modes, and failure rates. I just wanted to highlight as well, there is a bit of an intrinsic problem in the ISO 26262 concept. You saw the nice waterfall V systems lifecycle model earlier. This, of course, is applicable to, or we use that as applicable for our vehicle development processes. But of course, the supplier doesn't really have time to wait until we've got our requirements worked out to then start developing their system. They start a lot earlier and come up with what are effectively off-the-shelf solutions for us that we buy and integrate into our vehicle. So they will have to guess to some extent what we'll want to use the element for in order to determine the necessary processes, methods and tool appropriate for an ASIL that we might want to later on ask them to to provide. The same applies to the hardware failure rates. In order to calculate or know what a safe failure is or what failures I need to worry about, I need to have the concept again, because the failure rate calculation obviously only includes or doesn't include the safe failures, but I only know in the context of the bigger picture of the system what safe failures are going to be, and the same for hardware requirements. Sorry, I'm running out of time, so I'm just going to speed up a bit. I just wanted to highlight as well, it's not just, I think, at the supplier, although we appreciate that there are some challenges and complexities. For us, it's the other way around. At Jaguar Land Rover, we develop a range of vehicles. We've actually got, although we haven't got as many vehicles, different vehicles as some of our competitors, maybe especially the German competitors, but we also have different programs running on different vehicle lines, so we might have facelifts and updates. And we've gone to dividing up the functionality on our vehicles into features and systems now. So each vehicle consists of systems and features, and our functional safety process currently runs on these features and systems. Features might be shared across vehicles, they might be slightly different. They might be implemented across different systems. And again, as I said earlier, each system then consists of these components. So it might be a sensor, an ECU, an actuator. Sometimes these elements will be from the same supplier across the board. Sometimes for commercial purchasing reason, they might come from different suppliers. Managing the requirement cascade, and then again, the verification information we get back as we change, upgrade, and update functionality is becoming more and more difficult. This is also especially with a view to the ADAS and autonomous, although we're not obviously quite there at autonomous, but I think there's going to be a presentation later on that, because the interaction as well between system is becoming more and more complex. We've now got cameras telling the brakes when to brake rather than the driver, radar systems making the vehicle accelerate. This is changing also our ASIL classifications for some of our systems, which again adds to this complexity as I was trying to explain. So we might have a component validated, verified to ASIL A, but in our next program we already know, despite it providing the same functionality in principle, we needed to show or to meet an ASIL B integrity. Right, hopefully this has given you a bit of a summary of functional safety, design, verification in the automotive industry and some of the problems that we see from our view as OEM. The solution at the moment really is to try and predict what our uses of components are and sort of communicate that or budget for future use. But we are also seeing suppliers obviously trying to anticipate how their systems will be used, and quite often it's actually the suppliers who are further ahead in the sort of technology, what can be done, and come to us with possible solution. And yeah, as I've already indicated, this will become more challenges as we move towards driver assist and semi-autonomous functionality for the reasons mentioned before. Thank you.
Question at the front there.
So you were mentioning a few minutes ago that you're not involved in the hardware requirements of the components that go in, or the not even the fit rate or the allocation of you know, the FTTI. How could that be?
Yes, FTTI. Sorry, the question was that I meant. You thought I'd mentioned we're not involved in the hardware requirements.
Really and that you're not involved in that as an OEM. That's what I want to understand.
Yeah, no, so the question is whether we are not involved in the hardware design. Sorry, I need to repeat it for the web-based listeners. As an OEM, I did mention FTTI. That is something that we see as being set from the system level, but that might be broken down and allocated to different elements of a system. So yes, we are very much involved, definitely at the top level. Where it breaks down, it's where it starts getting complicated. There might be aspects of it that we do need to leave to the supplier to work out their own detail. And fit rates, yes, sorry, I didn't touch on those that much, but yes, especially for the distributed systems now, we do need to up proportion fit rates across the system. So yeah, no, that needs to be done.
So is there a move towards a more kind of distributed architecture within the vehicle where there's shared communications infrastructure, some kind of network or bus? And if so, how do you manage the possible consequences of sharing of that resource between different systems?
So the question is if there's a move towards a more distributed architecture and how we manage the sharing of distributed resources. That already exists to some extent at the moment on a what we call a level 0 car, so a car without driver assist system. The interactions are not as complex, but it is becoming more and more challenging, yes. And it's something that we're just trying to find the best processes for. I think ISO 262 doesn't really provide for these complex distributed systems. And unfortunately, even edition 2 isn't going to address it in any much different. Yes, but it's then, I think the question here aims at, as an OEM, we're putting more and more items on top of each other. And how do you argue about that the combination of the items is still safe? So I think at the moment, we're assuming if we put a lot of items together and they all individually work safe, you get a safe car because you've got the driver in control. And if each one of them fails individually, they all fail safe. But as soon as you put a driver assist system over there, you suddenly need to start about what if an item outside the scope of the assist feature item fails, can my assist system cope with it or not? And yeah, this is where it starts getting interesting.
Thank you, Edith.